Diffusion models are catching up big time for solving language tasks. In particular, I came across this paper called LLaDA, which is a diffusion model. It's an unprecedented 8 billion scale model trained entirely from scratch, and it seems to rival Llama 8 billion in performance. And they have shared this plot where the model seems to do equally well in mathematics, general task, Chinese, and coding. And they have compared it with Llama 3 8 billion base model and Llama 2 7 billion base model. The LLaDA 8 billion base model seems to be an all-round performer across mathematics, general task, Chinese, and coding. If you remember, in my previous video, we saw this model from inception. This was Mercury, and it was particularly focused on coding tasks. And we did this Super Mario game, and we also did this ball bouncing around the wall for the LLaDA model, which stands for Large Language Diffusion with Masking. They have given examples for quite a few tasks. For example, it's able to solve math problems, it's able to solve daily life problems, and it's also able to generate code, and it's also able to translate, for example, from English to Chinese. So in this video, let's read this paper on LLaDA and understand how they go about using a diffusion model to address language modeling. I quite like the motivation of the paper. They're saying that if you take the large language models, they have manifested this wonderful ability to scale, instruction follow, in context learning, and they can do conversations and even compress the large amount of training data that's fed into the model. And it all comes not from the auto-regressive mechanism, but rather from the core principle of generative modeling, which is approximating the true language distribution through maximum likelihood estimation. So if we look at the auto-regressive models, we give the input in sequence. For example, we pass Chelsea, and the model is going to predict the next word, which is the match. But nothing is stopping us really from sort of giving all these together. And if we pass all these three words together, the model needs to predict the next word, or it could be that, we're going to hide this word. So that's the main motivation behind challenging the autoregressive nature of these LLMs. So if we are given, let's say, data that's distributed like this, all that we are trying to do is that we're trying to capture the distribution of this data using, let's say, a distribution p of x, and which is parameterized by a parameter theta. And we're trying to model the distribution of this data, which can be captured by the best possible distribution p of x. And that is what the generative modeling is all about. If we have a model that captures this distribution, then we have the ability to generate infinite amount of data using this distribution. So that's what they're saying here. The key insight overlooked previously is that the generative modeling principles, rather than the autoregressive formulation, is what underpins the essential properties of large language models. But one of the challenges that underpins this autoregressive nature of LLMs is that they need to go sequential token by token generation, and this incurs high computational costs. Because we are dealing with data in a forward manner, it's not possible to do reverse reasoning. So these are the two main drawbacks, and particularly the high computational cost is what motivates us to think of a different way of with these LLM models, which is that of diffusion. And that is what this paper is proposing, which is LLaDA, Large Language Diffusion with Masking. So masking is the main idea in the paper. So let's look into what this idea of masking is and how they go about it. In contrast to traditional autoregressive models, what they're proposing is to use mask diffusion model, and it's not something new. Basically, it's been used in all these papers before, but in the context of images. But here they're saying that they can use discrete random masking, and they can train a mask predictor to approximate the reverse process. So similar to traditional way of training large language models, they're also following this pipeline where they do first data preparation, pre-training, and as a third step, they do supervised fine-tuning. So let's dive into each of the steps. So the pre-training step is quite simple. We have the input and we have t, which is one of these values, which is sampled uniformly between 0 and 1. Let's say we're sampling this one and this one. Those two are masked with a mask ratio or mask distribution, which is a uniform distribution. And then we have a mask predictor, which is going to predict the value of the mask here and here. And we can see that the model is predicting that. And with this simple logic, we are pre-training it. In the next step, which is supervised fine-tuning, we have the prompt and also the response. In this step, again, we also apply masking, but we only apply the masking in the response and we do not mask any of the prompt. And we use the mask predictor again to predict the mask. And obviously, because we have masked it, we know what the value is. We calculate a loss between the predicted mask and the actual value, and we train this. After that supervised fine-tuning step, the model is now ready to do inference. So during inference, they discretize the time steps that are involved. So what does that mean? So at time t equal to 1, we start with all the responses hidden or masked. At the next timestamp, the model predicts one value, and in the following timestamps, it goes on, and in the end, we can see that it has predicted all the responses. And this time step seems to be a hyperparameter we can choose. For example, here we have 4 masked tokens. So if t equal to 2, then in this step, it will predict 2 of the values. And in the next step, it will predict all of the masked values. If we take t equal to 4, then each of the time steps, it will only predict one of the masked values. Thus, the intermediate steps becomes one of the hyperparameters. And the next hyperparameter that they are using is that of the generation length itself. So if we take images are like fixed sizes. It may be a rectangle or it could be square. But if we take sentences, we have the number of words can vary. For example, we can have a very small sentence and we can have several tokens in a sentence. Because the length of the sentence varies when it comes to language, we need to tell the model that the generation length also needs to vary. And so they're specifying the length of the fully masked sentence at the beginning of the sampling process. So with that overview of training and inference, let's look into some of the experiments. So they have evaluated for scalability, instruction following capability, and in-context learning capability. So let's first start with scalability of LLaDA. This is the plot they are showing. Clearly, as the number of flops increases, we can see that LLaDA, which is shown by these stars, increases. That is also comparable to auto-regressive baselines such as llama models. And this behavior is seen across the board. For example, if you look at the MMLU or PIQA, whether it's a 0-shot or 4-shot or 5-shot, we can clearly see the same behavior, indicating that LLaDA is quite scalable as the number of flops increases, and that behavior exactly resembles that of the autoregressive baseline models. So we can actually use them for practical, highly scalable applications. Now, one of the next things that they demonstrate is the benchmarking on different results. So with those positive results on scalability, they've also shown some results on benchmarking and comparing them to Llama 3 and Llama 2 models, and they have kept the number of parameters equal as much as possible. For example, this is 8 billion and this is also 8 billion, and they've also compared with Qwen and Mistral and DeepSeek. They're all against 7 billion, so that the comparison is like for like. And we can see that on MMLU, LLaDA 8 billion is slightly performing better than the Llama models, but across the board we can see that the performance is very competitive, and this is with the pre-trained LLM, and they've also compare the results for post-trained LLM. So one thing to note is that LLaDA only employs supervised fine-tuning procedure, but the other models have reinforcement learning, which is quite a powerful technique to improve the models. It's not a surprise here that Llama 3 8 billion is doing pretty well because it's been fine-tuned with reinforcement learning, but still the values are pretty comparable and it seems to do a pretty good job. And they've also shown a brief comparison on the completion task, and we can see that LLaDA 8 billion instruct is very good in reversal, which is one of the advantages of this diffusion models. This result clearly indicates that when it comes to reversal, even GPT-4o or Qwen model are lagging behind, but LLaDA 8 billion instruct is pretty good in this reversal reasoning. And they are wrapping up the experiments with some case studies, and they are presenting the results of LLaDA 8 billion instruct in table 4. So let's look at table 4. This is the visualization of the sampling process and generated multi-round dialogue. For example, if the user asks, Lily can run 12 kilometers per hour for 4 hours. After that, she runs 6 kilometers per hour. how many kilometers can she run in 8 hours? Then LLaDA comes up with this answer. In 4 hours, Lily runs 12 times 4 equal to 48 kilometers. After 4 hours, she runs 6 times 4, 24 kilometers. In total, she runs 48 plus 24, which is 72 kilometers in 8 hours. Result is 72. And finally, they're just wrapping up with some conclusion and discussion. So I think it's a fairly simple paper. The idea is fairly simple as well. It comes down to masking, and this opens up a completely new chapter when it comes to large language models, which is that of using the idea of diffusion in order to train the large language models. I hope that was useful, and I will see you in my next video. Until then, take care.